Now in this video we are going to discuss how to find particular integral of a linear differential equation with constant coefficients. And as I said, the particular integral of such kind of differential equations is based on the right hand side, that is r, which may be a function of x or constants. So there are many different cases in which we apply different algorithms. So we have to discuss these cases one by one. So case first, if r is e raised to the power ax, that is r is an exponential function. So particular integral in this case, when r is an exponential function, 1 upon fd e raised to the power ax, 1 upon f a e raised to the power ax. That is, in fd we need to replace the coefficient of x in the power of exponential function. Suppose the equation is d2y upon dx square plus 3 dy upon dx plus 4y is equal to e raised to the power 5x. We need to write it as capital D square y plus 3 capital dy plus 4y is equal to e raised to the power 5x. Then taking y common out of it, we get d square plus 3d plus 4y is equal to e raised to the power 5x. So our fd is equal to d square plus 3d plus 4, and particular integral in that case 1 upon fd, and right hand side that e raised to the power 5x. So if r is exponential function, then we have to replace d by the coefficient of x in the power of exponential function. So 1 upon f5 e raised to the power 5x. So now fd is d square plus 3d plus 4. So we have to replace d by 5 here because we need to find f5. So 1 upon 5 square plus 3 into 5 plus 4 e raised to the power 5x as it is, and we get 1 upon 25 plus 15 plus 4 e raised to the power 5x, and 1 upon, taking sum of these, we get 44 e raised to the power 5x. And as I have said earlier, that here in this video we have to discuss only particular integral because we had discussed in the previous video the complementary functions, and in the coming video, that is the third video of this segment, we will discuss the complete solution of such kind of differential equations. Here there is a possibility when r is e raised to the power ax and pi is equal to 1 upon fd e raised to the power ax, integral as 1 upon fa e raised to the power ax, but sometimes fa is equal to 0. So in that case, the whole particular integral will be undefined. If this happens, then particular integral, that is 1 upon fd e raised to the power ax, will be written as x into 1 upon f dash d e raised to the power ax. Then we replace here d by a, so we get f dash a e raised to the power x. Then this will be the particular integral if fa is 0. And again, if f dash a is 0, then particular integral will be x square 1 upon f double dash a e raised to the power ax, and so on until we get defined particular integral. For example, if the linear differential equation is given as d2y upon dx square minus 6 dy upon dx plus 9y is equal to e raised to the power 3x, which may also be written as capital D square y minus 6 capital dy plus 9y is equal to e raised to the power 3x. Taking y common out of it, we get d square minus 6d plus 9 y is equal to e raised to the power 3x. Now, particular integral is equal to 1 upon f d into r, and r is e raised to the power 3x. So 1 upon f d is d square minus 6d plus 9 e raised to the power 3x. If we replace d by 3, 1 upon 3 square 9 minus 3 6 are 18 plus 9 e raised to the power 3x, that is 1 upon 0, because positive 18 negative 18 becomes 0, e raised to the power 3x. So this is not defined. So that means here f3 is equal to 0. As I said, if fa is equal to 0, then what we have to do, particular integral is taken as x. Writing x, we have to differentiate fd once, then e raised to the power ax as it is, and then we have to check whether f dash d is 0 or not. If again it is 0, then again we have to take one more x, that it becomes x square, and then we have to take one more differential of fd, and then we substitute e is equal to a, and if it is non-zero, it's okay, and if it is again 0, then we have to repeat this process again and again until we have a defined particular integral. So here f3 is equal to 0, so particular integral is written as 1 upon differential of d square minus 6d plus 9 will be 2d minus 6, and e raised to the power 3x as it is, and taking x out, because we have to take one power of x outside every time we differentiate the denominator. So this is f dash d, 2d minus 6. So now we check f dash 3 is equal to 3 2 is 6 minus 6, again it is 0. So we have to repeat the process again. Particular integral is equal to, it was x 1 upon 2d minus 6 e raised to power 3x. So one more x we have to take out, so it becomes x square, and again we have to differentiate 2d minus 6, so it becomes 2 only, e raised to the power 3x as it is, and obviously now this is constant and can't be 0. So this is our required particular integral, x square e raised to power 3x upon 2. Now case second, if r is of the form x raised to the power n, then particular integral, which is always 1 upon fd into r, turns out to be 1 upon fd into x raised to the power n. So in this case, we have to take fd in the numerator, so it becomes fd raised to the power minus 1 x raised to the power n. Then we need to expand this using binomial theorem, and then we operate those differential operator capital D on this function one by one for each term. For example, y double dash minus 4y dash plus 3y is equal to x cube is the differential equation to be solved. Taking y common out of these terms, in the bracket we get d square minus 4d plus 3 y is equal to x cube. So here fd is equal to d square minus 4d plus 3, and r is equal to x cube. So particular integral is equal to 1 upon f d r, that is 1 upon d square minus 4d plus 3, and r is x cube. So first we need to take 3 common out of this. We get d square minus 4d upon 3 plus 1 x cube, because before taking this expression to a numerator and expand it according to binomial theorem, we need to change it into binomial form, and for that purpose we need to take only the constant term common and consider the expression in d as one term and 1 as the other term, because it is convenient to expand in that case. So 1 upon 3, and taking this to numerator we get 1 plus d square minus 4d upon 3 raised to the power minus 1, x raised to the power 3 or x cube. Now we have to expand it by binomial theorem. So first 1 plus into minus minus d square minus 4d upon 3 plus d square minus 4d whole square upon 9 and minus d square minus 4d whole cube upon 27 and so on, x cube. Simplifying, we get 1 upon 3, 1 minus d square minus 4d upon 3 plus, expanding this by a minus b whole square, we get d raised to the power 4 plus 16 d square minus 8 d cube upon 9 and minus, expanding this by a minus b whole cube, we get d raised to the power 6 minus 64 d cube minus 12 d cube d square minus 4d on 27 x cube. Proceeding from this step, one thing must be kept in mind, that is degree of x. As we know, if degree of x is 3, its fourth differential and higher differential will be 0. So we need to take the terms of d up to highest degree 3. So we have to ignore in this expression d raised to the power 4, d raised to the power 5, d raised to the power 6 and higher powers of d, and we need to consider only the power of d which are either less than or equal to 3. So we take 1 minus d square minus 4d upon 3. In this expression, we have to consider only these two. So plus 16d square minus 8d cube upon 9. The next expression, this term is useless because this is sixth differential and sixth differential of x cube must be 0. And this is third differential of x cube will be constant, so it is considerable, minus 64d cube. And in the next terms, we get d raised to the power 5 when we open up this bracket. So fifth differential will also be 0 of x cube, and d cube into 4d will get 4d raised to the power 4. That is the fourth differential operator. So fourth differential of x cube will also be 0. So we need to ignore rest of the terms. We take only 64d cube upon 27. That's why we have not written the next terms of this binomial expansion, because next term will have higher powers of d which are useless for calculating particular integral. So in that way, be very careful about taking the powers of d. So now we have to simplify this 1 upon 3, 7 LCM. Here we have 27 minus 3 9s are 27, 9 d square plus 9 4s are 36 d plus 9 3s are 27, 3 will multiply 16, 48 d square minus 3 8s are 24 d cube, and 27 will divide 27 one time, and here minus into minus plus 64 d raised to the power 3 bracket close x cube. So simplifying, we get now 1 upon 81. If we multiply all these terms by x cube, so we get 27x cube plus 36 dx cube plus 39 d square x cube plus 40 d cube x cube. So 1 upon 81, 27x cube as it is, plus dx cube, that is first differential of x cube, that is 3x square. So 3 will multiply 36, 3 6 is 18, 8 1 carry, 3 3 is 9 and 1 10, 108 x square plus d square, here 39 d square x cube. So d square means second order differential of x cube. So that is first order will be 3x square, and second order differential will be 6x. So we get 39 into 6x. Then next 40. Third differential of x cube, that is second order differential is 6x, then third differential will be 6. So we get 6. 1 upon 81, 27x cube plus 108 x square plus 6 9s are 54, 5 carry over number, 6 3s are 18 and 5 23 x plus 6 4s are 24, 240. Now taking 3 common out of these terms, we get 3 9x cube plus 3 3s are 9, 3 6s are 18 x square plus 3 7s are 21 and 3 8s are 24, 78x plus 80 upon 81. So this 3 will cancel 81 27 times. So finally our particular integral is 9x cube plus 36x square plus 78x plus 80 divided by 27. That's it. Now third case of PI is, if the right hand side of such equation is of the form sin AX or cos AX, then PI, which is equal to 1 upon FD, function on the right hand side of the equation. But in the case of sin AX and cos AX, we write the function FD as FD square. And the value of PI is obtained by replacing D square by minus A square in FD square. And if F minus A square is equal to 0, then PI will be equal to x 1 upon f dash minus A square sin AX or cos AX. That means taking x outside, we have to take the differential of FD square, making f dash d square, and then we replace d square by minus a square. Again, if f dash minus a square is equal to 0, then pi is equal to x square. One more x is taken out, and we have to take the next differential of fd square, and we have to replace d square by minus a square and sin ax or cos ax. Now let us take an example. Say d2y upon dx square plus 6y is equal to sin 4x. So the left hand side may be written as d square y plus 6y is equal to sin 4x, and taking y common, we get d square plus 6y is equal to sin 4x. And as you know well, PI of linear differential equation of higher order is obtained by 1 upon fd, this expression, and the function on the right hand side, but we have to write down this expression and sin 4x as it is. So as we have explained that in the case of sin ax or cos ax, in fd, d square is replaced by minus a square, and here a is 4, so a square is 16, so we have to replace d square by minus 4 square plus 6. Then sin 4x is written as it is. Now 1 upon minus 16 plus 6 sin 4x, that is equal to 1 upon minus 10 sin 4x. So simply minus 1 upon 10 sin 4x. So the second example is to solve the equation d raised to the power 4 plus 2a square d square plus a raised to the power 4y is equal to 8 cos ax. So this expression we denote by fd, but in the case of sin ax and cos ax, we denote it by fd square. So fd square is d raised to power 4 plus 2a square d square and a raised to the power 4. So in that case, pi, that is particular integral, is equal to 1 upon fd square, and the function on the right hand side 8 cos ax. Since 8 is a constant, so it should be taken out, and we get 1 upon fd square cos ax. So 8 1 upon fd square, that is d raised to the power 4 plus 2a square d square plus a raised to the power 4 cos ax as it is. So in that case, we replace d square by minus a square. But before replacing d square by minus a square, we need to check whether f minus a square is non-zero or 0. So f minus a square, that is, this d raised to power 4 may be written as d square whole square. So minus a square whole raised to the power 2 or square plus 2a square, and here d square, so minus a square plus a raised to the power 4. Simplifying, we get minus a square whole square a raised to the power 4, and we open up this bracket, then these two signs will multiply, minus 2a square into a square a raised to power 4 plus a raised to the power 4. So 2 positive a raised to power 4 and 2 negative. So when f minus a square is 0, we need to differentiate this expression, that is fd square. So p I is equal to 8, and when we differentiate it, we take x out, and after that we differentiate this as 4d cube plus 4a square d. Derivative of a raised to power 4 is 0 because this is constant, and cos ax as it is. So now again 8x 1 upon 4d cube may be written as 4d square into d plus 4a square d as it is cos ax. Now we have to replace d square by minus a square, but before doing so, we need to check it whether f dash minus a square, that is replacing d square by minus a square in derivative of fd, which is 4d square d plus 4a square d. So that is 4 replacing d square by minus a square, this d as it is, and after that plus 4a square d. So simplifying, we get minus 4a square d plus 4a square d. Obviously these two terms are identical and having opposite signs, so will be cancelled with each other and we get 0. So again we have to take derivative of this expression, and doing so we need to take one more x outside. So we get pi is equal to 8 into one more x is taken out of this expression, so it becomes x square, and then differentiating this expression with respect to d, we get 12 d square plus 4a square cos ax. So now 8x square, and now replacing d square by minus a square, and obviously this time this expression cannot be 0. So 12 minus a square, replacing d square by minus a square plus 4a square. So 8x square into 1, 8x square upon, here we get minus 12a square plus 4a square, or 8x square, sorry, we forgot to write cos ax here. So cos ax, 8x square cos ax upon, here minus 12a square plus 4a square, 8 minus 8a square is left, 8 is cancelled by 8, and ultimately we get minus x square cos ax in the numerator, and in denominator only a square because we have taken minus as common. So this is pi of this differential equation. Now the next case, that is fourth case, is f dy is equal to e raised to the power ax into phi x. So in that case, our particular integral will be 1 upon f d e raised to the power ax into phi x. That is, the function on the right hand side of a linear differential equation of higher order is product of two functions in such a way that one of the factor of this function is an exponential function and other one is any other function. So rule to find particular integral of such kind of function is we need to take this e raised to the power ax out of this expression, and then we need to replace d by d plus a, and we put phi x as it is. Then we have to apply whichever case is appropriate for this particular function, because this is arbitrary function. It can be an exponential function or algebraic function or trigonometric function. So whatever function is this, according to that we have to take our next appropriate steps. Now let us take an example for understanding this particular integral. So here f dy is equal to e raised to the power x sin x. So this is the product of two functions. One function is exponential function and other one is sin x. So the same situation, e raised to the power ax phi x, that is phi x is sin x here in this particular problem. So we need to apply this condition. So our particular integral is equal to 1 upon f d e raised to the power x sin x. So we need to take e raised to the power x out, and doing so we need to replace d by d plus 1, because here coefficient of x is 1 and sin x as it is. So e raised to the power x 1 upon, now f d is d square minus 5d plus 6. So in this we need to replace d by d plus 1. So we get d plus 1 whole square minus 5d plus 1 plus 6 and sin x as it is. So e raised to the power x, and first we need to simplify this. D plus 1 whole square is expanded as d square plus 2d plus 1 and minus 5d minus 5 plus 6 sin x as it is. So now e raised to the power x 1 upon d square 2d minus 5d minus 3d, 1 positive, 5 negative, 6 positive, so 7 positive and 5 negative, so plus 2 is left, sin x e raised to the power x. Now we need to replace d square by minus a square, and here a is 1 because in the angle of sine there is x, so coefficient of x is 1. So you may say that a is 1 over here, so a square is 1, so minus a square means minus 1. We have to replace d square by minus 1, minus 3d as it is, plus 2 as it is, sin x. So simplifying we get e raised to the power x 1 upon, and here we get 1 minus 3d sin x. Now what to do when a linear function of d is left in the denominator? So we cannot replace d square by minus a square because there is no d square. So in that case we need to multiply numerator and denominator by conjugate of this expression. So we need to multiply here numerator and denominator by 1 plus 3d. So in the numerator we get 1 plus 3d, and in denominator we get 1 square minus 9d square, because if we multiply this by 1 plus 3d, so we get the situation of a plus b, a minus b. Using that we may write 1 plus 3d into 1 minus 3d as 1 square minus 3d square. So we get 1 minus 9d square sine x as it is. So in the next step, e raised to the power x as it is in the numerator, 1 plus 3d as it is in denominator, replacing d square by minus a square because a is 1 and a square is 1. So minus a square is minus 1. So replacing d square by minus 1, we get 1 plus 9 because minus into minus becomes plus, and sine x as it is. So now it is 10. So e raised to the power x upon 10 and 1 plus 3d sine x. So e raised to the power x upon 10. If we multiply this sign inside this bracket, we get sine x into 1 plus 3d sine x. d sine x, derivative of sine x. So e raised to the power x upon 10 sine x as it is plus 3 as it is. d sine x, as I said, is derivative of sine x, which is cos x. So cos x, and that's it. This is the pi of given differential equation of second order. Now the next article is to prove 1 upon d minus alpha into q is equal to e raised to the power ax integral e raised to the power minus ax into q dx, where q is some function of x. So let's prove it. Let 1 upon d minus alpha q is equal to v. So transposing d minus alpha to right hand side, let it be equation number 1 first. Then we have to transpose d minus alpha to that side. We get q is equal to d minus alpha v. So we may write it as d minus alpha v is equal to q, and then we open the bracket, we get dv minus alpha v is equal to q, and here dv, as you know well, d means the operator d upon dx, so it becomes dv upon dx minus alpha into v is equal to q, where q is some function of x. Clearly this is a linear differential equation in v and x, so we need to compare it with the standard form dv upon dx plus p, v is equal to q, p is equal to minus alpha, so integrating factor is equal to e raised to the power integral p dx, so that is equal to e raised to the power integral minus alpha dx. So integrating factor is equal to e raised to the power, as minus alpha is constant, so should be taken out of integral sign. So inside the integral 1 dx is left, so e raised to the power minus alpha into x, we get e raised to the power minus alpha x as integrating factor. So solution of this linear differential equation will be v into integrating factor is equal to integral q into integrating factor dx. So v into integrating factor is e raised to the power minus alpha x is equal to integral q into e raised to the power minus alpha x dx. Now obviously this may be written as v upon e raised to the power alpha x is equal to integral e raised to the power minus alpha x into q, because product is commutative, so q into e raised to power minus alpha x may also be written as e raised to power minus alpha x into q dx. So transposing e raised to the power alpha x to right hand side, we get v is equal to e raised to the power alpha x integral e raised to the power minus alpha x into q dx. Finally, from equation number 1, we replace v by 1 upon d minus alpha q here in this equation. So in the next article, we need to prove 1 upon d plus alpha q is equal to e raised to the power minus alpha integral e raised to the power alpha x into q dx. So we may prove in the same way as we have proved the previous one. So we need to assume V is equal to 1 upon D plus alpha Q. Let it be equation number 1. Transposing D plus alpha to left hand side, we get D plus alpha V is equal to Q. Opening the bracket, we get dV plus alpha V is equal to Q, and obviously dV may also be written as dV upon dx plus alpha V is equal to Q. So again, this is linear differential form which may be compared with dV upon dx plus S plus PV is equal to Q. So comparing this with this standard form, we get P is equal to alpha and Q is equal to Q, obviously. So integrating factor in that case will be e raised to the power integral P dx, that is e raised to the power integral alpha dx. So that is equal to e raised to the power alpha x. The solution of this linear differential equation format, that is dV upon dx plus alpha V is equal to Q, is given by V into integrating factor is equal to integral Q into integrating factor dV. So here V integrating factor is e raised to the power alpha x is equal to integral Q into e raised to the power alpha x dV. So this should be transposed to right hand side. We get V is equal to 1 upon e raised to the power alpha x integral, and this may also be written as e raised to the power alpha x into Q into dx. Sorry, here it should be dx, not dV. Dx. So V is equal to 1 upon e raised to the power alpha x may be written as e raised to the power minus alpha x integral e raised to the power alpha x into Q dx. So from 1 we have V is equal to 1 upon D plus alpha Q. So replacing here V by 1 upon D plus alpha Q, we get 1 upon D plus alpha Q is equal to e raised to the power minus alpha x integral e raised to the power alpha x to Q dx. So we have proved the required condition. One more important thing, many times most of the students requested me to upload some related videos after watching one of my videos, and it makes me very encouraged when they requested me for the videos which I had already uploaded on my channel under different playlist. So I request you all, please visit my channel and check out my playlist. There may be a lot of videos which are useful to you. So please like, share and subscribe. Take care, stay home, stay safe. See you next time. Wassalam.